All right. Good morning, everyone. Thanks for joining us today. We're here for another ECE colloquium. And for those of you that are registered for 801, please remember to mark your attendance for today as well. I want to make sure that we get that done. But without further ado, I want to jump into introducing our speaker for today. Dr. Benjamin Riggan will be talking to us about perception-based biometric recognition, challenges demanding unconventional solutions. So Dr. Riggan is an assistant professor with the Department of Electrical and Computer Engineering at the University of Nebraska-Lincoln, where he has worked there since fall 2019. And prior to joining the university, he was a research scientist at U.S. Army Research Lab, or ARL, in the Networked Sensing and Fusion branch. His research interests are in the areas of computer vision, image and signal processing, and biometrics forensics, especially related to domain adaptation, multimodal analytics, and machine learning. And I think another important fact about Dr. Riggan is that he graduated from NC State. He got his BS degree in computer engineering here in 2009, and then the master's and PhD degrees in 2011 and 2014 from NC State. So after he finished his PhD, he was awarded a postdoctoral fellowship at ARL's image processing branch. He also has 3 Best Paper Awards, and I will not butcher the names of the conferences. I'm not in the field, so but I think already the fact that you've got 3 of them is a pretty good testament to the quality of the work that you do, and I'm sure we'll see that today. And I also want to mention that he's an associate editor for IEEE TAES. So I've been informed that you're welcome to ask questions as we go along or keep them for the end. And with that, I'd like to invite you up to give your talk, Dr. Riggan. Thank you very much for joining us.
So we'll get situated here with all the wires. Can everybody hear me? All right. So, as was already mentioned, I'll be talking about perception-based biometric recognition, which is one of the primary areas that I work. Before jumping in, if I can get my clicker to work, I just wanted to talk a little bit about my lab. So the lab that I have is the Image and Signal Analysis Lab. And so, again, part of what I do is domain adaptation, computer vision, biometrics, forensics. So you can kind of see some of the samples of the types of work that we do. So a lot of imaging, but not purely imaging. You can see some of the seismic acoustic along with the imaging work that we do. A lot of multimodal analytics, face detection, face recognition, working in early childhood education, applying computer vision and machine learning in that aspect. There's also a project that I have with the Lincoln Zoo on tracking cheetah behavior and analyzing that. So there's a lot of stuff that my group, and I'll say primarily my students, work on as well, and helping drive a lot of this work. So for the outline, first I just want to talk a little bit about biometrics, provide an introduction, discuss some of the problems and motivations, and then we'll jump into some of these challenging problems that maybe we'll explore some unconventional solutions for. And this is a lot of the work that I've done since joining the University of Nebraska. So biometrics, there's a lot of biometrics out there. There's face, fingerprint, palm prints, iris. There's biological biometrics, DNA, soft biometrics, behavioral, things like re-identification, which we'll talk about a little bit, and things that use facial attributes or attributes of the biometrics themselves that can help strengthen these stronger biometrics. Anthropometrics, the physical measurements of the body from imaging systems, being able to discern that information. So that's what we're talking about when we talk about biometrics. A biometric has a clear definition. This has been proposed a long time ago by Neil Jain from Michigan State University. And so a biometric must be universal, meaning that every person has that characteristic. It must be distinctive. The trait is sufficiently discriminative, and it must be permanent, so there's some degree of invariance. And it also we must be able to collect it and measure it. So that's what we talk about when we talk about biometrics, but there's also a lot of interesting problems. We want the biometrics that we measure, that we collect and discriminate to be reliable, but now we start bringing in aspects of privacy and security. So how do we balance these things? We want to be able to recognize each individual in certain domains like law enforcement, Department of Defense applications, even commercial settings where you want to make sure that certain employees with privileged information are the correct individuals accessing that information. So where's this balance between privacy and security? And so I have a short clip.
Our main story tonight concerns facial recognition, the thing that makes sure my iPhone won't open unless it sees my face or the face of any toucan. But that is it. Facial recognition technology has been showcased in TV shows and movies for years. Denzel Washington even discovered a creative use for it in the 2006 action movie Deja Vu.
We have facial recognition software?
Yeah.
Let's use it on the bag, cross-match it to all the bags on the south side of the city in the 48 hours leading up to the explosion, all right?
Don't think it's ever been used this way.
Look, same thing. Bingo.
Bingo indeed, Denzel. With smart, believable plot development like that, it's frankly no wonder that Deja Vu received such glowing IMDb review.
So
As an insult to anybody.
we'll stop it right there. But you can see that there's a lot of jokes around facial recognition and the capabilities of, it is kind of crazy. Apply facial recognition to recognize this bag. It goes on to talk about facial recognition for fish and animals and things like that. So there's a lot of joking around facial recognition. But there's also serious concerns, right? So when we talk about machine learning, estimating bias in the machine learning models is a challenge. You've probably all heard that facial recognition is inherently racist. There's ethnicity biases and gender biases that even if you normalize the data sets to be equitable in all of those categories, that somehow the machine learning model, through its nonlinearity, it still ends up being biased in some way or another. Also, there's a huge concern regarding spoofing and deep fakes. So if time permitting, I have some work that we'll discuss on presentation and attack detection. So now let's jump into the technical part of the talk. So again, we're going to try to hit three interesting problems in this area of biometrics. One is heterogeneous facial recognition. The second is person re-identification. And time permitting, we'll talk a little bit about presentation and attack detection. And then just try to sprinkle in some of these challenges that we need to think about and maybe some unconventional ways to overcome them. So what is heterogeneous facial recognition? The idea is that we want to match two faces and facial images from two different domains or alternate imaging modalities. And this was put forth by Brendan Clare and Anil Jain. Brendan Clare is the CEO of Rank One, provides premier facial recognition software for law enforcement agencies around the country. And so in this idea of face recognition, we can look at this in multiple ways. We can think about it as a one-to-one match or facial verification. Am I who I claim to be? It's either I'm enrolled in the biometric system, I present my face. This is much like unlocking your iPhone. You claim to be the owner of the iPhone, you present your face, and it unlocks. If you're not the owner of the iPhone, it doesn't unlock, unless, of course, it's one of your children. Then it'll unlock. Then there's the rank retrieval, so a one-to-N match. In this case, we have a closed set gallery of employees or somebody enrolled in a DoD watch list. And so given the probe image, here the probes are shown as a thermal image, you want to be able to retrieve the correct identity out of that closed set. But the assumption is you assume that the image that you present is contained within that gallery. And then there's the one-to-N open search. This is where you start to reject that this probe may not exist in that set. So open set recognition. So varying levels of complexity there. And so when we talk about heterogeneity, we can think of it in terms of photo to sketch. We can think of it in terms of the electromagnetic spectrum. We can think about surveillance cameras, near infrared to visible imaging, or we can even think about in the days of COVID, thermal imaging to visible imaging. So a lot of the literature out there, we've seen in COVID, thermal imaging has been popped up in supermarkets and stores just to measure your temperature. And they say, oh, we're not looking at private information, we're not looking at faces, but the capabilities, hopefully I'll show you, is there, that you can actually discriminate and learn who's who, and even just from a thermal image. But there's a lot of applications. So we can think of heterogeneity in terms of various conditions. So high resolution to low resolution, if you're familiar with super resolution. Varying expressions, these are more classical definitions for facial recognition. Variety that we might want to address, varying expression with frontal images. One of the most challenging conditions, which I'll show later, is still handling the pose. It's not, pose invariance is one of the most difficult things to address, and having to do this simultaneously while bridging a modality gap or that spectral gap is really difficult, and demands some new approaches. So the main motivator for heterogeneous facial recognition is all of these real-world challenges: variable illumination, low quality matching, off-angle pose, false detections. So when you look at the system as a whole, you can build the recognition part of it, but if you're getting all of the noise in the detection and looking at the system as a whole, that's a real challenge. And then bringing in the presentation attack detection, cosmetics. The use of everyday cosmetics can thwart a facial recognition system really easily. So with that introduction into heterogeneous facial recognition, I want to largely talk about one class of approach. And so this was a paper one of my PhD students worked on and was presented at a IEEE Biometrics conference, IJCB, and still continue this. This is kind of the topic of his doctoral work. But when we look at this, we're primarily looking at long wave infrared to visible facial recognition. And prior to this work, not only did we look at using machine learning to help us do what is really difficult for a human, and studies actually have shown that in a population of 100 subjects or more, only about 25% can pick out the correct identity out of a gallery size of 4 individuals. So that's pretty significant of how challenging it is to look at a thermal image and look at the gallery of visible images and make that match. So now you start scaling that to larger gallery sizes, it becomes significantly more challenging. And so a big motivator for thermal imaging comes from military applications. So DoD, Army, Navy, Air Force, the intelligence community, CIA, NSA. And so a lot of times they're interested in covertness. So as you move to long wave infrared, those longer wavelengths, you gain covertness, but you really degrade the quality of similarity between the images. So that's a fundamental challenge. So one way early on in this type of work that we approached this was leveraging physics in addition to machine learning. So we looked at polarization imaging, leveraging polarization state information to help bridge the gap. So you can see this degree of linear polarization image on the far right. And so notice that this is an emissive image. It's fully passive, no active illumination required, but the polarization state and the degree of linear polarization ends up bringing out the geometry of the face, and it ends up being more highly correlated with the visible image. But there's challenges in the design of these sensors. This particular image was acquired with a polarizer that was rotating at a certain frequency. So now you've got non-time synchronized Stokes vectors. So Stokes vectors meaning S0, S1, S2, the various orientations of the filter and the combinations of those orientations. So you have the horizontal and vertical and the diagonal components. And you can normalize those to generate this image, the degree of linear polarization. But with those sensor designs, you're always giving up something. You're either having an asynchronous design, where you're capturing these Stokes vectors at different points in time, so motion artifacts become a problem. You could also consider like a bare pattern with these micro filter grid arrays on the CCD elements or the thermal imaging sensing elements, but then you're giving up resolution, which is critical in thermal imaging with this emissive patterns. So ideally, even though the polarization state information helps and is well correlated, there's these physical challenges that have to be overcome. And one other challenge that I need to mention is it changes with the perspective of the face with respect to the viewing axis of the camera. So the signature of the image is actually going to change, whereas with a regular visible image, largely, other than noise and lighting and shading, the illumination stays this constant. So we don't have that as strong of a challenge there with visible imaging or with conventional thermal imaging. So ideally, we would like to address it with conventional thermal imaging sensors and then be able to boost and overcome this correlation from the polarization state information. So this slide here shows you the degradation when with varying wavelengths. So the image on the left is two separate visible images of the same person, and you can see how largely across the face the structural similarity. When you move to a little bit longer wavelength to near infrared, still largely correlated. You get some degradations. A lot of that's due to the saturation of the near infrared illumination. Short wave infrared, again, largely correlated. These are all both reflection dominant regions of the electromagnetic spectrum. Then when you start to move to the emissive portions, the mid-wave infrared and long wave, notice the discriminative parts of the face lose the correlation, the eyes, the nose, the mouth. And so this is the gap that we're trying to overcome. We want the same individual from both of these modalities to match well, but we also want to discriminate across different subjects, and preferably for a large population size. So how do we do this? There's a couple of different strategies in doing this in the machine learning community. One, we could just aim to learn robust representations and in order to make our inferences. In more recent years, generative adversarial networks for synthesizing images. We might use generative models, and it doesn't have to be generative adversarial networks. There's other generative models that we could use, but the idea of we want to take a thermal input image and produce a visible-like image for matching. And there's trade-offs here. One, if we have control over the inference engine and the recognition system, we'll opt for option one. If we don't have control over the facial recognition matching, option two is the better approach. So I do want to point out there's trade-offs. We opt for the former, but again, I want to emphasize that there are limitations to this in practice if you don't actually have control over the matcher. So, and there's been a lot of work in all of this domain. And so there's a group from Johns Hopkins University that has worked heavily on the generative adversarial network-based approach and synthesizing these images. My group has done a little bit in this domain as well, but largely the bottom half of this, the deep perceptual mapping, coupled neural networks, we've tackled this type of approach. But that's the prior work. So now what have we done since then? So again, we're still largely looking at this robust representation, invariant representation that we want to learn. And so here's sort of the general framework that myself and my student put forth. So again, we extract the representation from both of these modalities. Inherently, even if you are looking at the same features, the quality of the image is going to have a degradation in the quality of the representation that we need to bridge. And so we do this with a transform-based technique, but more so, it's in the driving forces that are optimizing this network. And so part of the contributions that we looked at were modifying existing architectures and modifying them in strategic ways, exerting control over the system so that we at least have some idea as to what's going on. And then, again, learning that transform through these objective functions to get forth what we actually want the system to learn. So one of the first things that we did was a feature ablation study of where are the most common features. So unsurprisingly, if you follow conventional machine learning literature, early features that are looking at edges and corners are much more robust and generalizable across multiple domains. As soon as you get to the deepest layers of the network, now you're over-tuning and being more responsive to the detailed texture. So now think about a visible image that has rich texture and geometry that's not present in the thermal image. So naturally, we don't want the visible representation to be dependent on that because it's not there in the thermal image. So the way that we tackled this is just removing those higher layers. So in one sense, because of the reduced parameterization, this is very fast to execute. But now we have this huge representation curse of dimensionality to deal with. So again, lots of challenges. All of these things are interdependent and interrelated. Every decision that we make. And so we have to control that system. So, but given those features, we've gotten ourselves at the most correlated representation for the network that we can. Now, we want to transform the thermal representation in some way. And so we use a residual spectral transform that we design. And so one of the novelties here is we're doing this locally. We assume that whatever transform we apply at one part of the image is going to be applied at another part of the image. So that's one of the big assumptions. And largely, the reason we did that is because the degree of overfitting in this type of multi-domain or cross-domain application, domain adaptation, we're exponentially going to overfit faster. And so, again, think about your conventional wisdom in machine learning. Number of parameters sort of dictates how much data you need to learn those parameters, and the degrees of variation add to the complexity of how much data you need. The more complex the variation, the more invariant you want the system, more data. So the way that we're looking at this problem is, well, we don't want to just say that we need more data. We need to look at it in a more rigorous manner. So now we get to the driving force of the system. So a lot of domain adaptation methods function off of minimizing like a mean squared error between the embeddings. That's great, assuming you've got synchronized, precisely co-registered images, all of these variations, right? In the real world, we don't have that, especially when we start looking at off-pose to frontal matching, keeping that in mind, that we're not always going to be sitting down in the DMV taking a thermal image. So we want to be able to bridge this gap. So now we're looking at this from the filters that our classifier are using. So the main idea here is that you want to take the visible filters from your classifier, keep those filters fixed, and then do your cross-entropy optimization, but with the thermal representation. So now, and we're not updating the classifier, so the only way that the system has to adapt is by bridging that representation in this high-level, task-level manner. So that was the approach that we took. And it turns out it works pretty well. We also added a little bit of a domain invariance loss just to help regularize the system. And so this is just the idea of we want to predict. Normally we could easily predict, given a visible image, that it looks more visible-like. Given a thermal image, it looks more thermal-like. But we want to do the opposite. We want to make those things roughly the probability given either visible or thermal image is roughly equal to half. Equal probability that we're confused as to which domain it was drawn from. So that just kind of helps, and it has nothing to do with identity whatsoever. So that just helps us sort of stay in this optimization space. So how did we evaluate this approach? So this has been ongoing research for years. So when we started out, small subject pool, 60 subjects, not a lot of data by comparison. Visible data sets, you've got MegaFace that has millions of identities, billions of faces. So we're not working with that, but yet we're working with this complex domain, so we had to demonstrate something. Over time, we slowly got more and more subjects, so bridging 100, and I'll show you a larger data set. But here's that feature ablation study where you look at different layers of the network. And so largely for this particular data set, which is registered to a 200 by 200 size image around the face, we found consistently across most networks, after about 3 convolutional blocks is where we get the most correlation, because we've got enough nonlinearity at that point, but not so much that we're overfitting to the rich textures of the visible. But then you see the degradation once you go beyond that. And so we've done a lot of analysis. I'm going to kind of skip through this. So we've compared it with other types of transforms. We've looked at it with and without the regularization techniques. And so, again, we just sort of exert control at every step of the way. So we looked at expression and pose, but now look at pose. With the expression, we're getting very high rank 1 identification. But with the pose condition, that off-pose thermal image matching a frontal DMV style passport photo image, we're still getting very low performance. We've made improvements over other transforms and techniques in that way, but still a lot of work. We also contributed this larger data set, nearly 400 subjects. The evaluation set compared to protocol 1, which was, we did a 50-50 split, so 30 subjects in the evaluation set. Now we use 100 subjects. So now we're kind of getting at least some realm of scalability. And we've also added a lot of complexity in the variations. So all the details of the data set are here, but I want to point out, so baseline, I'll point out that the PIX-to-PIX, GAN VFS, and D et al. Are all image synthesis-based approaches. And then ours is the row in bold, and then you can kind of see the baseline, visible to visible level of performance. So we're sort of edging on in the frontal to frontal matching in this cross-domain sense, very close to the visible face verification results, equal error rates, within a couple of percent of frontal to frontal visible-based matching. And we also looked at expression. Again, frontal varying mouth doesn't have a huge effect. Pose analysis. Again, we're still getting the best compared to these image synthesis-based methods, but it's still not as high. There's a huge degradation. So we've made advances, and just recently, I didn't include them in this slide, but this is the problem that my student's addressing now. We're currently writing a journal paper where we've been able to address this even further and get it closer to the levels that we're seeing in the frontal to frontal matching and bridging the spectral gap. So, and ultimately we want to put this into a system where we detect the face, detect the landmarks, register the face, and can pick out the subject. And so you can kind of see the example here. So I don't want to spend too much more time on facial recognition, but you can kind of see some of the physical challenges and how we work our way at just chipping away at understanding the problem, both from the physical and explainability side and also from the machine learning side. And so one of the things that we haven't looked at yet is now can we bring that physics back in with the polarization state information? We don't know. That's largely unanswered at this point. And there's a lot of values in terms of invariance, the surface materials that you get with using this imaging phenomenon. So the question I'd like to pose is, if we're getting this good of performance, is there a value to using this type of thermal imaging system and replacing it? Well, one thing is cost. Cost is a big issue. Currently, sensors are slowly coming down in price and getting higher and higher resolution, but they're still always going to be that cost factor. But there's a lot of value compared to the visual clutter that you get in visible imaging. Thermal imaging, at least largely in indoor settings, you're going to get a lot fewer false detections because there's less thermal clutter. Now, outdoor during the day, there's going to be a lot of thermal clutter. So there's a lot of challenges, and you can kind of see some of the synthesis results in terms of quality of given the emission-based representation, what we end up with. So now, really quickly, I want to jump into another form of biometric. So this is a little bit more soft biometrics, and this is person re-identification. So person re-identification is the idea of that we have a query that we want to use. There's somebody that we're looking for. It could be a missing child. It could be there was some event like the Boston bombing, and we have this suspicious individual, and now we want to see and build a timeline of where they've been, find that person of interest. What were they up to before that? Where did they go after? And same thing for the missing child. Where did that missing child go when they were last seen? And so we want to be able to search camera networks to find those individuals. And so really in this case, we're dependent on the query. We don't necessarily know who that person is. In the case of the missing child, we know the missing child's name. But the idea is if 10 people walk into a building, can you figure out in which order they come out? So that's why it's re-identification. There's not really that strong identity need for an identification or a name. And so there's loads of applications for this in terms of finding missing children, commercial security, surveillance, law enforcement. So this is one tool that's very valuable. And so there's been a lot of work in this domain. We're definitely not the first to address it. But the one thing that we are interested in, and a lot of it stems from the prior application, multimodal data collection. A huge part of my life has been spent annotating and curating data. And so if we can make that easier, that's a huge value to the community. So most of the re-identification literature is all supervised-based machine learning. You know the identity of the individual. And so we want to take a different approach. There's lots of challenges in this space when people change clothes. If I take off my jacket, put my jacket on, as you can see here. Improper detections, again, looking at it from a holistic system perspective, because before we can do re-identification, you've got to know where each person is in the camera network across these video streams. Occlusions, people occluding people, carrying objects. There's all these different optical effects. I had to throw this in there for Nebraska. You know, it's a big football community, as is NC State. And I told them I bleed a different kind of red when they hired me. So, but, you know, I had to jump on board the Nebraska bandwagon. It was part of my, they made me sign a letter. But Same clothing, right? Re-identification is largely based on visual appearance. And the most visually discriminating things is you're wearing a red shirt, I'm wearing a blue jacket. That's easy to discriminate. Machine learning models, if they can cheat, they will. So we've got to overcome that challenge. So now we want to add in another challenge. We want to do this without labels. We want to be able to do this in a completely unsupervised way. And so, again, another one of my PhD students, this was actually work that he did as he was a master's student. And so this was part of his master's defense, is how do we build a system that's fully unsupervised and able to cluster this representation so that we can get this very discriminative representation. So again, we start just like a lot of machine learning. We leverage convolutional neural nets, but we inject this unsupervised attention. Majority of attention models out there, again, supervised. The idea that if you know which class or which individual this person is, that is in this image, you can then figure out which pixels lead to that decision. Okay, what's ultimately the driving force behind a classifier? There's a similarity metric or a dissimilarity metric that we have to drive. So clustering is all about these metrics. So if you can define the right metric in which to cluster, you can then track that back to pixel changes. And that ultimately gives you your attention. And so we want to leverage that attention in order to filter out all the noise, all the things that are irrelevant. Focus on what's important. So we ended up building both channel attention, so which filters are most relevant, and spatial attention. And also, we aren't using hard labels, we're using just our best guess at pseudo labels. So we do all kinds of augmentation, standard machine learning things. But then with our loss function, we start to train on these augmentations, and then we build what we call a memory bank, our cluster centers, and we build an objective function around that, which looks a lot like a supervised classifier. But we use the cluster centers as the weights in our classifier, and we drive the representations in our associations. So it's kind of like k-means. You have to take your data, associate it with some cluster, you drive the representations towards that. But it's in this more complex, and ultimately we're using this simultaneously to learn the attention in an unsupervised way. And so it looks like this hierarchical clustering because over time we merge the clusters together. So we start off with every image is its own cluster. And then we start to slowly merge these based on their similarity, but then we update the representations for their assignments, so on and so forth. So when doing this, we analyze this on several data sets. But in table 2 particularly, when you do this completely from scratch, if you use some of the conventional approaches, I mean, you're getting things 10%, 8%, 9%. It's not discriminative whatsoever, but now rank 1, 53.6%, mean average precision, nearly 30%, well above what anything else is providing. If you provide a little bit of supervised pre-training, which again, we don't argue is unsupervised, you're using some supervision from another task to gain some discriminability, it doesn't mean it's not something good to do. You can certainly do it. It's a fair thing to do. But again, when you're dealing with thermal imaging or more complex modalities, what are you pre-training on? It's something that's completely irrelevant to the domain. Is it going to be helpful or harmful? Probably more harmful. So things to consider. The Duke MT-MC dataset, same thing. We're sort of getting closer and closer to the level of supervised performance in this re-identification domain using a completely unsupervised approach. And so we can actually look at our attention maps. So if you look at the state of the art at the time, the bottom-up clustering, it's paying attention to things in these images that aren't even the person, especially when we get those poor detections. But even when the person is in the field of view, where it's paying attention to the discontinuities in the image. When you use another approach was the convolutional based attention model, it gets a little bit better. It's at least driving away from the edges of the image. There's still some response at the edges of the image, but then just a subtle response at the person. But then when you start to look at the attention model that we propose, it gets more holistically the person. And this is all done unsupervised. We also looked at the complementary nature of our attention maps because we use group convolutions and things like that. And so you can also see the separability that we're gaining. So compared to bottom-up clustering on the left, you can see these groups of identities that we've circled that are cluttered and obscuring one another in this visualization of the high-dimensional representation. But then we get better separability in the TS&E plot on the right using our attention model. And so we can look at, again, the different effects. If we look at specific queries in the middle of these four cases, the greens are the ones that correspond to the correct individual, to the query. The reds are the false positives that are returned. And so a lot of false positives. But again, using this more attention, unsupervised attention, we can increase that discriminability of the system. And we've done this, we've extended this work and added a couple of other novelties, but I'm not going to go into that right now just because I want to get to the last problem. So again, we've done a lot of extensive analysis on the supervised. We've done this for video-based and image-based data sets, which is big for, I'll stop here really quick. So bottom-up clustering, our original approach, and then now here's our latest approach. So you can sort of see the progression in terms of the approaches. But again, fundamentally, the two are the same. One of the differences is the complementary assumption that we have in the latter approach is able to pick out finer detailed features like shoes. So if you're both wearing a red shirt, white hat, beige pants, I don't know if that's fashionable or not, but different shoes, that's a discriminative factor. And so that's one of the things that this latter approach picks out on and is able to enhance it in that way. And again, completely unsupervised. And so you can kind of see some of the visualizations there. And again, enhanced attention of being able to pick out. And so you can kind of see it here. We're able to pay attention to the feet in a lot of these cases of the individuals. So, and handle a lot of variation without any labeling at all. So real quickly, I'll spend 5 minutes on this. Presentation attack detection that I alluded to earlier. Real challenge. So we have things, so related topics to presentation attack detection, if you've ever heard of anti-spoofing or liveness detection. And so this can be applied in all kinds of biometrics. Face, fingerprint, iris, some of the soft biometrics. And so there's various types of presentation attacks: masks, glasses, cosmetics, print and replay attacks. And so we looked at this in a couple data sets. We've collected our own. And so again, I'm going to skip some of this, but I want to kind of point out this plot again. We always look at, how separable and discriminative the features are in the representations that we're getting. And so on the left is a traditional visible-based presentation attack detection system. So we're only using visible imaging. And you can see, okay, the video and photos are really separated from our genuine faces, our bona fide representations, which are the blue dots. But the face disguise and the fake face are really obscuring those bona fide representations. So it would be really hard to tell the difference between those two. One of the reasons that the video replay attacks and the photo attacks are so discriminative here is because of the optical effects. There might be a reflection, something that the machine learning model can pick out on. And so it's almost counterintuitive. You would think if I show a very photorealistic picture of a face and try to present it to a facial recognition system, that would be hard to discern. But what the machine learning model is paying attention to turns out to be quite the opposite. So, but then when we apply this type of domain adaptation approach where we want to enhance the quality of, given a visible image, we want to discern whether or not this face is real or not, we get better separability. Notice that now the bona fide faces are largely clustered here. You have some other types of attacks that are clustered here, and you've got some bona fide faces that pop up there, maybe a couple up at the top too. But largely, comparing the two, much more separable. And again, this is all driven from domain adaptation. So now, we've talked about a lot of challenges. Scalability is one thing to keep in mind. How do we reduce the representation sizes? How do we boost the match rates and sort of populating as much information through the system as we can? Because a lot of times time matters. How quickly you get your matches matters. And there's a trade-off. So we looked at truncating the network. That gives the feature extraction, that part of the process is really fast, but the match speed is really slow because we have this huge embedding size. So we could trade that off and have a longer feature extraction time, and arguably we could parallelize that feature extraction and then reduce the embedding size to make the match speed fit faster. But are we sacrificing any discriminability when we do that? Maybe yes, maybe no. Depends on how we design the system. Standoff distance, pushing the acquisition range out to 1,000 meters. So the caveat with the facial recognition is we were operating at a distance of about 3 meters. It's not very far. A lot of pixels across the face. So that was the part I waited to the end to tell you. You know, I wanted you to be impressed up front. But atmospheric turbulence. When you take a visible image from a long distance, especially on a hot day, what do you see? You see the nonlinear atmospheric turbulence effects. Time varying. Real challenge. Extreme pose. We saw the pose. Like I said, we've just been able to mitigate that. And like I said, I'll save that for another time. You can hopefully read our paper once it's accepted. And then this bias. Again, I didn't really talk about the bias much. It's there. Some of this, because of the limited data sets, these data sets are not balanced for gender. They're not balanced for ethnicity or socioeconomic status. There's all these challenges. Sensor costs I mentioned. And so these are really niche applications, but what I argue is that it spans beyond the DoD and the intelligence community. Because if you can remove the clutter in the holistic system and get fewer false detections, that improves the whole system perspective. And also I mentioned the more qualitative, the resolution mismatches, the quality mismatches of your imaging. It doesn't have to be thermal. And so one of the biggest limitations is lack of data. And so again, I mentioned that I spent a lot of my time just curating data for these applications because off-the-shelf data sets aren't addressing these problems largely, or they might be addressing it in very little chunks. So that's another way to contribute. And so ultimately, with domain adaptation, we want to address this domain and covariate shifts between the representations from the physics and the statistical aspects. And so that's something else that I'll leave you to ponder over. We have a limited collection. So usually domain adaptation is applied to data set, different collection environments. You want to address the gaps in that domain. So we could have a modality domain adaptation, but we also have collection conditions that might be biasing what information is actually learned. So ultimately, we want to understand and model the phenomenology and these conditions and be able to mitigate them. So whether we use physics-based modeling, sensing, like the polarization state information, the synthesis of complementary information, also, again, the direction that we're pushing is how do we do this without biasing through labels? It's hard. It's really hard. But if we can do it, we're not saying that it's ever going to be better than if you had labels. That's not what we're saying. But if it can help you have a very complex multimodal data collection, and you can, from that raw data or minimally processed data, get some degree of how easy or difficult the data set is, that's valuable. Because that might inform you of, do you need to collect more data? Do you need to change the assumptions about the problem that you're working on? And then also distributing the process, distributed learning, decentralization, and consensus across everything. We want to reduce the number of sensors. We want to extend their range. We want to make it real time. All these nice things. But again, we do it incrementally and exerting as much control as possible. So, with that, there's a list of publications here. So I will take questions. I know I covered a lot of material really quickly.
You showed in one slide that you could also detect videos from real faces. So how about deep fake videos?
Deep fake videos. So that was part of the. We didn't explicitly include deep fakes, but we used the physical fakes, so like a mask and like that. Deep fakes are hard, but there are underlying statistics. If you look at the data, there are subtle cues that make it not realistic. And so right now, machine learning has a challenge at detecting this. There's some literature out there that focuses on this, but largely it's an emerging area because it's a competing battle. The deep fakes are getting better, and then the presentation attack gets better, and so it's this teeter-totter. But yeah, we haven't specifically worked on that problem, but there are individuals that are. And again, it usually comes down to micro expressions. That's the difference. Or weird generative artifacts. But the generative modeling is getting better, and it's getting scarier.
Can I add one more query?
Mm-hmm.
You have tried adversarial attacks on the model?
Yes, we've tried adversarial attacks, and largely, again, it depends on the realism of the attacks. But typical noise doesn't seem to affect the model, especially in the frontal case. Now, you start doing weird distortions to the pose, that's where you're going to see the adversarial attacks be successful.
So there was a lively mission about the bias when doing prediction of genders and races as well. Can you? I'm just curious about what techniques are there that can distinguish bias from these new inducements between gender and races?
So the person that you really want to, or if you're really interested in this area, Kevin Boyer from Notre Dame is like the leading expert in bias estimation. But in an attempt to answer your question, usually what they do is the old approach was to just balance the data set. But we know through the nonlinearity, it's not going to stay balanced. So really, they track the covariant shift through the network, and they try to make that equitable at the inference decision, if that makes sense. So that's the typical approach to try to mitigate bias. You're not going to completely remove it, because again, it's one of those real challenges. And then one of the other questions that Kevin Boyer tends to ask is, okay, you want to recognize faces, right? So what's the most discriminative feature that the face is in these facial recognition systems is looking at geometry and texture of the faces. So edges across the face. Well, if you have somebody with darker skin complexion, those edges are more subtle, right? So one of the things that we need to do is balance that out. How do you make the edge response and that shape response, which is ultimately what we use in the recognition system, and make it equitable across skin tones? And same things male and female, different geometries. There's something there that makes it, more biased towards males than females. And it's not just a matter of lack of collection. So I don't know if that answered your question. Okay. Any other questions? We have time for maybe one or two more, depending on the length.
When you say bias, what do you mean?
So,
I don't know if I completely understand that.
So when you're looking at the probability of making an error, you're more likely to make an error when presented a female face than a male face. Or you're more probably going to make an error with, if you have a model trained on only Asian faces, right? You're going to have a higher probability of making a mistake on a Caucasian face. So, but even if you balance those across, Asian, Caucasian, African American, other ethnicities, or male, female, you balance that at the input, you're still going to you're going to have a preference towards one set or the other. And that's a bad thing, especially in terms of the error, right? So that's what we mean by bias.
Do you see a strong age bias?
There is age biasing as well, yes. So obviously with infants and toddlers, we've seen that with the iPhone in the news. I think they've largely corrected that, but I think it's still present just because of, similarity in facial features within families, but also elderly. So, the extremes of the age distribution are largely not covered. And again, think about the machine learning model. It's minimizing the expected loss. If most of your energy is in the middle age group, you're going to be biased towards that, right? Inherently. But again, if you normalize that in your training, you're still going to end up with a bias and a preference towards one or the other.
So do iPhone 12 to 15 use 3D options for the face recognition?
So, in my experience, 3D information, the value it adds is in normalization of the geometry in the pose. Discriminative information from the 3D representation adds very little, if any, if that makes sense. So the texture and the appearance, so when you combine the 3D frontalization and 3D normalization of the face with the 2D processing, that's when you tend to have the biggest bang for your buck. Now, there are papers out there that, we'll say you get a few % extra with 3D information, but, I'm thinking at a high level. Yeah, and part of it might be a challenge with bigger representation. Maybe we need more data in that domain, and collection in that domain is hard to get the truth, right? You have depth sensors, but there's sensitivity issues. I think the 3D MD is probably one of the best sensors out there in terms of getting the face. There's some LiDAR representations, that data sets out there. But again, they're small in scale, not huge population sizes. So I think if we scale them, I agree, it might add a lot of value. But I don't think we have the data yet to support it.
So the iPhone does not use it?
The iPhone they do structured lighting. They do structured lighting. And again, if I were to guess, they're normalizing the face in terms of geometry and then using conventional matching techniques. But that's obviously, I don't work for Apple, I don't know. But, if I were to guess. So that's just conjecture.
Let's not pass it forward.
All right, I think we're over time. But
More questions? All right, if not,
thank you.
All right, Ben. Thank you for the visit.
Thanks, Hamid. It was wonderful catching up, and we'll be in touch.
We'll